Hi everybody, so now we're going to do the last part for the lecture for chapter 16. So this has to do with how heat moves. So let's look at this picture and you're going to see there's different parts to it, but there's one thing that's the same for all of them. So here for the flame, this is the hot section, and the air around it, that's going to be the cold section. And you find that heat is going to travel from hot to cold here. And even for the pot of water, so here, this is the hot section of the water. This is the cold section of the water. And you always notice that the bubbles in the water always flow upwards. So heat here in this case is flowing from hot to cold. From the handle as well, this is the hot part of the handle. And then your hand is going to be the cold part. And you always get burned because heat travels from the hot handle to your hand there. So that's going to be the first concept, is that heat always travels from hot to cold. And there's different ways that heat moves. The first one is by direct contact, by touching. So this is called conduction. So this is how you get burned, because you have to touch something to get burned, or a pot to get burned. The next one we talked about before when we looked at plate tectonics, and it has to do with, for example, imagine that this is the core of the earth, and we said that lava rises, and it hits the surface of the earth, and it cools down, becomes a rock, and then as it cools, it sinks, and then it gets heated at the core, and then it rises up again. Same thing happens with water. The hot water, the bubbles, they heat up and they rise. As they rise, they cool down. And as they cool down, they sink. And as they sink, they get heated up again. And as they get heated up again, they rise, and then the cycle repeats. So this idea of convection we're going to talk about again in the next couple of chapters. So convection just has to do with circulating fluid. And the other one is radiation. So let's see how this one works. So if you look at here, this is the Earth. You can see the Earth has a thin atmosphere, so this is where all the gases are. So this is where weather happens in this thin layer here, actually probably even more towards the bottom. And outside here, this is outer space, where you have the vacuum of space, which means that there's no air here. So the sun sends its energy, but the energy doesn't need any air to travel through. It can travel through the vacuum of space. And this kind of energy is called radiation. So the sun warms the earth through radiation. So the next form of way that heat travels is by radiation. And radiation can travel through a vacuum. And this is how the sun warms the earth. Or how the sun transmits energy to the earth. So you can look at our spectrum. Well, actually, let's go back here for a second. Let me restate this. So if you look at a rainbow involves a part of the sun's energy or radiation that we're used to seeing, which are the visible colors. You can see here it starts from red to orange, yellow, green, blue over here. And same order here, you have red, orange, yellow, green, blue. So the light that we see is actually part of a bigger range called the electromagnetic spectrum. So let's see how this works. So really what the electromagnetic spectrum is, it's or light in general. Light is a wave, and it's a wave created by electrons that are vibrating up and down. And as the electrons vibrate, they send out two things. They send an electric field that vibrates up and down, and they also send a magnetic field that vibrates side to side. So because of that, we call light and microwaves and radio waves, we call all of those things an electromagnetic wave. So what makes a radio different than light? So if you look at a radio wave, it vibrates up and down, but it has a longer wavelength. The top of one wave to the top of another is longer, and it vibrates slower. So that's what a microwave looks like. And so how is light different than a microwave or radio wave? Is that light vibrates faster. So light vibrates faster, it has a shorter wavelength and a higher frequency. It vibrates faster. And how about X-rays and UV? Why are they so dangerous? Is because they vibrate very fast. They have a lot more energy, and that's what makes them more dangerous. So light then is part of a bigger quantity called a spectrum. So this is light here, visible light, but it's part of a bigger spectrum that includes radio waves, microwaves, infrared, visible, all the way down to X-rays and gamma rays. And so radio waves, they vibrate really slowly, they have a long wavelength. Light vibrates very fast, and X-rays vibrate even faster, and they have a shorter wavelength. And the size of a visible light wave is about the size of bacteria, which is why you can use microscopes to look at bacteria. I would also recommend that you take a look at this video here, because this is a really good visualization and broad overview of the electromagnetic spectrum. So here, there's nothing highlighted. Yes, I covered everything here. So here there's nothing highlighted, but we're just gonna kind of discuss this just in order to preparation for the next part. So if you have the surface of the Earth, the sun sends in its energy, but its energy gets bounced off in different ways, so that only about half of the sun's energy ever reaches the surface of the Earth. Part of that hits the cloud and it gets bounced off back into space, and part of it just gets scattered by the atmosphere. So we're gonna get into how the Earth gets heated by the sun, and we're only gonna talk about the part of the sun's light that actually hits the surface of the Earth. And let's actually go back into this idea here of what happens to the sun when it hits the atmosphere. So the sun sends its light, and as the light interacts with air molecules, it actually bounces off the blue light in every direction. And because of that, the blue light pervades the sky, and that's what makes the sky look blue. So now let's look at an important application of what we just talked about, which is the greenhouse effect. So let's zoom in here. So this is the Earth, and then this is our atmosphere. What you find is that the yellow light from the sun, it vibrates at a high frequency, and it's able to pass through our atmosphere and hit the surface of the Earth. As it does that, it's going to heat up the surface of the Earth, and as the surface of the Earth heats up, the Earth is going to emit its own radiation, which is going to be infrared. And infrared vibrates at a longer frequency, and this longer frequency gets trapped by carbon dioxide in our atmosphere, and those carbon dioxide atmospheres re-release that heat, and that keeps the Earth warm. So this is what actually helps the Earth to have a warm atmosphere. So let's just kind of put this together piecemeal. So carbon dioxide and also water vapor. I'm just going to write CO2 and just water vapor. What they do is that they absorb infrared radiation from the surface of the Earth. From the warm Earth's surface. I'm just going to say from the surface of the Earth. And after it absorbs it, it releases that heat to warm the atmosphere. So then it releases the heat to warm the atmosphere. And so this is what keeps us warm, is the fact that, so let's look at some extremes here to put this in perspective. This is the moon. The moon has no atmosphere, so the yellow light from the sun comes in. It warms the surface of the moon, so the moon surface gets really hot. But since there's no gas to trap it, all of that heat just leaves, so the moon goes to extremes. The light regions are going to be very hot, and the dark shadows are going to be very cold. And let's look at another extreme, which is going to be Venus. So Venus, excuse me. So Venus, same process happens. The yellow light from the sun comes in, and it's going to warm the surface of Venus. But Venus's atmosphere is 97% carbon dioxide. So once the surface of Venus warms up, it's going to emit infrared. And here, since there's so much carbon dioxide, the atmosphere is going to trap all or most of the heat from the infrared, and that's going to make Venus very hot, so that the Venus is actually about almost 1,000 degrees Fahrenheit, night and day, all year round. So let's look at the Earth then and see what happens. So on Earth, we only have about 0.04% carbon dioxide. So the same process happens. The yellow light passes through the Earth's atmosphere, and it warms the Earth's surface. And that warm surface releases infrared, and that infrared gets trapped by carbon dioxide, and that carbon dioxide releases the heat back out, and that keeps our atmosphere warm enough that we can have liquid water on the surface of the Earth and not frozen. Or, well, yes, we can have liquid water so that the Earth isn't cold like the moon, so that any water would be frozen, or it's not hot like Venus, so that any water would boil away. Okay, so we just have one more slide to go, and this one has to do with how where you happen to live affects temperatures. So here, this is a picture of Canada. You have two cities. One of them is by the ocean, and one of them is inland. And if you look at the temperatures in those two cities, and they're also at the same elevation, so that shouldn't affect temperature. But let's look at what happens to how the temperature changes in those two cities. So what you find is that in Vancouver, that's going to be the red line, it's cold in the wintertime, and it's warm in the summertime. But if you look at Winnipeg, in wintertime it's even colder, and in the summertime it's even hotter. So they're at the same latitude. So the only thing that makes a difference is that Vancouver's by the ocean or by water, and then Winnipeg is inland. So what you wind up finding is that something else that affects your climate is the terrain. So coastal cities, they have they're not too hot and not too cold. So that means that they're going to have smaller temperature changes. And then if you live inland, it's the other way. You can go from very hot to very cold. And you have large temperature changes. So another thing that affects, this is still relating to the same concept, but now let's look at, let's go back to something that we talked about before. And this has to do with the fact that the southern hemisphere is about 80% water, and the northern hemisphere is about 60% water and 40% land. And here this is about 20% land. So what you find, since the southern hemisphere is mostly water, it's going to be more stable. The temperatures aren't going to rise that much, or they're not going to change as much. So in the southern hemisphere, since it's mostly water, the temperatures are going to be more stable, so it's going to have less temperature variations. Okay, so this concludes the lecture for chapter 16.